Good afternoon, everyone. I warmly welcome you all to this prestigious event commemorating 100 years of Bose Einstein Statistics in the Mahamana Seminar Complex Hall of the Institute of Science. As we come together to commemorate the centenary of Bose Einstein Statistics, it is a great honor to welcome our distinguished speakers, Professor Umakant Rapol and Professor Partha Ghosh. We are also privileged to have with us our esteemed Dean of the Faculty of Science, Professor S.M. Singh sir, respected faculty members from various departments, and dear students. This program celebrates the centenary of the monumental contribution to the world of physics by Professor Satyam Bose. To begin, I invite the Dean, Faculty of Science, to formally welcome our distinguished speakers of today by the offering of rosebud. Please welcome our guests with a round of applause. As is the tradition of our university, I invite our speakers to offer a floral tribute to Mahamana Pandit Madan Mohan Malviya, the visionary founder of Banaras Hindu University, as we pay respects to his everlasting contribution. I request Dean sir to please accompany them. One 100 years ago, in 1924, Professor S.N. Bose authored the final of 4 revolutionary publications that shaped the course of the modern quantum mechanics. His work laid the foundation for what we now know as Bose Einstein statistics, giving rise to an entirely new field of study. In recognition of his genius, half of the fundamental particles in the universe were named after him, bosons. This discovery paved the way for many significant advances in physics, with several Nobel Prizes later being awarded for works related to bosons. Today, we honor the legacy of this visionary scientist, whose contributions continue to resonate in every corner of modern science. To formally begin our program, we have the privilege of hearing from Professor Shiru Rai Chaudhary, who will provide an introduction to the legendary scientist, Professor Satyam Bose. Please join me in welcoming Professor Shiru Rai Chaudhary.
Respected Dean sir, respected department, distinguished guests, our very honored speakers, in particular Partha Ghosh, who has been a mentor and a friend to me for I don't know how many years. It is a pleasure and an honor to be asked to speak a few minutes in memory of that great scientist of India, Satyam Bose. I will be brief because you are actually anxious to hear the speakers. But still, I would like to take a few points regarding Bose in his work and to clear a few common misconceptions that are on the internet and are given to word of mouth. Now, the first thing I want to emphasize is that Bose's actual contribution is to have pioneered what we call quantum statistics, which involves a new way of counting the microstates of a system. The earlier only one method was known, that of Boltzmann, the method of Boltzmann, where states are counted in a particular way, and that leads to the Maxwell-Boltzmann statistics. It is Bose who first thought of doing this counting in a different way, and that is now textbook material. Now, as is well known, he sent his paper to Einstein, and Einstein was immediate. I should mention that he first sent it to a journal for publication, and in a story which is familiar to all of those who do research, the journal sent it back after some time saying it's not worth even publication. But then he sent it to Einstein, and it was Einstein who immediately recognized the importance, the novelty, and the brilliance of this work. And one reason for that is that Einstein himself had been working on the same problem. Not only Einstein, but some other very well-known scientists, whose name I will mention shortly. They had also been working on the same problem, but without success. Now here came the solution from an unknown person in an unknown part of the world, at least then. Now, Einstein generally was a person who developed his own ideas, and then others followed him. You know, there are only two occasions in his life when he took somebody else's idea and followed it. The first was when he was a very young man, unknown then. Then he took Max Planck's idea of the quantum and used it for the photoelectric effect. That was the first time. The second time was when he took S.N. Bose's idea of counting on macrostates, and he went ahead and developed it into what I call the Bose Einstein statistics. So I should make it clear that the textbook version of the Bose Einstein statistics, which includes chemical potential, was developed by Einstein in a single author paper. But he acknowledges that he used the method of Bose. And as a follow-up of that, he discovered what we today call Bose Einstein Condensation. So it was not Bose who discovered Bose Einstein Condensation, it was Einstein who discovered it, but it is called Bose Einstein Condensation because Einstein could not have done it without the pioneering work of Bose. So that's the first thing I'd like to say. The second point is that many people think that Bose got his idea by doing a clever piece of mathematics. The answer is no. That mathematics was known for several hundred years. In fact, it was in the algebra textbook which Bose had studied as a student, and it is there in most algebra textbooks today. No, it was, the problem was to understand the black body spectrum. Well, classical theories had failed. Now we all know that in 1900, Planck had obtained some way of getting this by assuming that energy is quantized in packets of h nu. But nobody understood how this can happen because light was a continuous wave. Now Planck himself thought that this quantization, or this making of energy into packets, it is done by the emitting body. It is not a property of light itself, but it is an induced property due to the body which is emitting it. And that was implicit in his, the way he obtained it. Now, after that, of course, Einstein showed that once the light comes out in packets, it remains in packets and is absorbed in packets. But the fact that light is a continuous wave can become also packets, this is something which they could not understand or imagine. Their imagination was confined to the emitting body, saying that that is putting out light as packets. Now, many people had tried to develop a theory of this that included very famous names like Debye, Nathanson, Ehrenfest, Campbellianus, Pauli, and of course Einstein himself. He developed this theory of spontaneous emission and absorption, which people study in laser physics. It's still used, but it is not a theory of the light itself. It is Bose, who was working in isolation, who was able to make the leap of imagination that the behavior of photons is their own property. The particle property is a property of light. It is not a property of the emitting body. This required a leap of imagination which all these other famous scientists did not been able to achieve. It was Bose who got it. Now, of course, if quantization is a property of light itself, we already know that light has a wave property, then wave-particle duality is already there. So, Bose, he used this. Perhaps he did not realize how deep his intuition went, but he was the first to say that light has a purely particle nature as well as that of a wave. And of course, we understand that only today in terms of quantum field theory. It is amazing that Bose also used three very, very important results of quantum mechanics, which were then developed by others in the future. They give the credit for having made those discoveries, but they were all there in Bose's work. The first one was the uncertainty relation. Delta x, delta p is equal to h, or approximately h. This was part of Bose's derivation. Only 2 years, 3 years later, Heisenberg discovered it. Heisenberg had very good arguments for it, which Bose did not have. But it is Bose who used it the first time. The second thing is that he also used the de Broglie relation. The p is equal to h by lambda. This relation was also used by Bose for the first time. De Broglie had used it a little later, and de Broglie's relation came to be. And the third one, which you will hear more about from Professor Bosch, is that he also had the idea of spin. The fact that a point particle can have a spin in quantum mechanics was another realization which came to Bose. Unfortunately, Einstein himself could not believe it, and so he removed it from the paper when he translated it in German. But Bose was the first to think of it. So it's amazing that three ideas, all of which were awarded the Nobel Prize in the years to come, were all there in Bose's work. And yet, as you know, the prize did not go to Bose. It's a real shame that so many prizes came out of, Nobel Prize came out of Bose's work, but he was not given the prize. The third point I wish to make is that if you look at the internet, you will find a lot of writing that Bose was responsible for the discovery or the prediction of the Higgs boson. You will find his name in connection with the Higgs boson. Now, I'd like to say that there is very little connection between the Higgs boson and Bose himself. The reason that credit for the Higgs boson goes entirely to Higgs and to others who predicted it with him, not to us. And because S.N. Bose discovered an entire world of new particles which are called bosons. The Higgs boson is just one of them. You know, to take an analogy, America, the new continent, was discovered by Amerigo Vespucci. It is named after him. Inside America, there are other cities like Pennsylvania, which is named after William Penn, or Nashville, which is named after Francis Nash, and so they are named after individuals. Now, nobody says, why is Pennsylvania not named Amerigo Pennsylvania? No, it's not needed. Because Amerigo Vespucci discovered the whole continent. So it is similarly with Bose. He discovered the whole world of boson. His discovery was much deeper, much more fundamental than just one particle. So that I think we should realize that Bose does not need to be identified with the Higgs boson. It's already there in the name. And to just say, try to claim that he should be given the credit for Higgs boson is actually bringing him down. His meaning, he was much greater than that. And the last and final point I would like to make, I have also read and heard from people. Bose, though he made this discovery of Bose extensions, after that what else did he? Or kept. Now, actually Bose, a lot of people think Bose for the rest of his life, he just enjoyed being a celebrity and he didn't do his work. That's not true. He actually worked very hard on his life, but he was not one who liked to publish it. If he had solved a problem, then he would just put it aside. He would only publish if he thought he had something really important and novel to say. Which is very different from today, because people publish even when they don't have something important to say. Now, in any case, this is a very, very narrow-minded view. After all, do we ask, what did John Dalton do after he proposed the atomic theory? We don't ask that. Do we ask, where did Neil Armstrong go after he went to the moon? We don't ask that. Do we ask, what did Tulsidas write after rupturing Banaras? We don't ask that. Once you have made a contribution which is so fundamental, so deep, and so important, you are in the Hall of Fame forever. well, what else you did in your life, even whether you lived or died, does not matter. You have become immortal. And that is how we should consider, and that is how we should honor Satyam. We should remember him for this one great achievement which opened up the entire world of statistics. And that is what we are here today to honor and to remember and to acknowledge. So on that note, I will finish, and I was really anxious to hear the speakers. So thank you very much.
Sir, thank you very much for sharing with us such wonderful historical facts about the legacy and works of Professor S.N. Bose. It's my pleasure to introduce our distinguished speaker, Professor Umakant G. Rapoor, an accomplished experimental physicist renowned for his pioneering contributions to quantum technology. Professor Rapoor is currently serving as a professor in the Department of Physics, IISER Pune. His research spans in the fields of atomic physics and quantum optics. His innovative works in the field of quantum information processing using atom-plasmon coupling, atom interferometry with Bose Einstein Condensate, and quantum chaos experiments have made significant advances in these cutting-edge areas. Today, we are fortunate to hear from him as he shares his insights on the impact of Bose-Einstein statistics on present-day science, exploring how this century-old concept continues to influence modern physics and technology. Please welcome Professor Umakant Rapoor.
Thank you very much for the kind invitation and also kind introduction. I'll try to do my best to impress upon you as to how the Bose-Einstein statistics has led to creation of what is called as a Bose Einstein Condensate, which was predicted long ago. And I will not get into too many historical aspects because there are more experienced and experts here who can talk a lot more about it. But I'll try to give you a small flavor of it and how actually one can and focus more on the Bose-Einstein condensate part of the entire the consequences of this statistics, which was invented by Professor Bose. Okay, so as our previous speaker, Professor Sri Upadhyay already mentioned, so the way of looking at classifying different kinds of particles that exist in nature, everything more or less can be summarized by this particular table, which essentially describes a lot of particles that exist in nature, and they are broadly classified into two big buckets. Okay, and I mean, I have taken this from Wikipedia. I mean, this is a standard classification, and so far the best physical model that explains the universe, the standard model of physics, it kind of predicts all of these particles. So if you look at this tree, there are two major branches. In the sense, there are two big broad classifications of particles, and those are what we now call them as fermions and bosons, naturally, because I mean, and this is mainly classified based upon the spin that the spin these particles possess. Either it is integer spin or half integral multiple of half integer spins. Now that's where you have this basic fundamental classification of these particles, and this is the tree which is described by, I mean, this is a tree of particles that is basically described by the statistics that was developed by Bose and which was later adapted and modified and whatever and done by Einstein to make it into a broader model to describe all these different types of particles. So basically you have the half integer spin particles and the integer spin particles. Now when we talk about these two particles, as I said, so you have the fermions which possess basically half integral multiple of spin, half, 3/2 and so on, and bosons which are these particles which possess spin either starting with 0 and 1, 2 and so on. If you look at the fundamental difference between how these particles, the statistics of these particles behaves in the sense that what is the, when we look at the statistics of any of these particles from a statistical mechanics point of view, you look at what is the occupation of these particles, the number of particles that these particular particles occupy in a given small energy interval. And when you write that down by doing all the mathematics, you arrive at this kind of occupation relationships for the number of particles in the ith energy state, and you look at these distribution functions which basically differ by just a plus or minus sign here, okay, and that makes a huge difference in terms of how these particles behave and how they don't behave. Now this is where it makes a difference. Now, you look at the particles which behave the Fermi-Dirac statistic, which obey the Fermi-Dirac statistics, and the particles that obey the Bose Einstein statistics. Now, for fermions, what happens is that as you start putting these particles, if you have a container with n energy levels and you start putting these particles together, as we know that fermions, another thing that leads to very specific characteristics of fermions, the Fermi-Dirac statistics, is because of the Pauli exclusion principle. That these particles, although they are indistinguishable and identical, they possess this spin half or multiple of half, which also has to obey this Pauli exclusion principle, which leads to this kind of a distribution function, which basically at you have basically one particle occupying one single energy level, whereas for a Bose particles which follow the Bose Einstein statistics, you can have many particles occupying the lowest energy level. For if you have to say that given energy level can be occupied by many of these particles. So that's a basic difference. Again, this is all the pictorially represented here. So if you have a container and you try to put in electrons in that container, and this container can basically hold particles with there are different allowed energy levels in this container. So you can have basically, well, this is a small mistake here. So you have only 2 particles per energy level, up and down spin, whereas in bosons, sorry about that, I forgot to remove them. So in bosons, you have all the particles, there is a possibility of all the particles occupying this particular, the lowest energy state. And that's called that's the state of matter where all the particles occupy a single energy level, and you get into a state called as a Bose Einstein condensate. And I will tell you some interesting features about then what one can do with these. Now, how to understand the formation of Bose Einstein condensation, this is a simple picture which one can imagine what is going on when the condensate is formed. So at say room temperatures, you have these particles hitting against each other, and if you look at the de Broglie wavelengths, corresponding de Broglie wavelength, they are so tiny compared to the size of the particles that you just don't see any effect of that. But as you keep slowing down these particles, the de Broglie wavelength starts increasing, and you will see that the average energy, average distance between the particles, the separation between the particles, the distance, that starts becoming equivalent to the size of the uh, wavelength associated with these particles, or the fuzziness associated with these particles, the de Broglie wavelength. Now you keep reducing the temperature, or you keep reducing the velocity further and further. What happens is that these waves start overlapping with each other, and at some point you go to a state where all these waves add up coherently and you get one giant wave packet. Now this is what would happen at very close to absolute zero temperature. Now this is what happens when you take matter through a Bose Einstein phase transition. Now, okay, I will not tell much about the historical aspects because I realize that there are experts who know much more about this, and we just heard about how the statistics was developed by Professor Bose and how it was taken forward by Einstein and leading to this particular paper. And like Professor Sri Rai Chaudhary already pointed out, it's about counting the way these particles are counted. And this particular paper, which was published in German, which was basically promoted by Einstein for this journal to be published, is basically it's about looking at the possible number of distributions that these quanta of light can be defined or can be counted in these small macroscopic cells whose size is of the order of h cube. So the way the counting is done, that kind of leads to the formulation of this distribution function for these bosonic particles. Now if you look at the consequences of, so for a long time there was no understanding or thought about how this particular phenomena, how this phase transition, or how matter can go into such state can be realized. Now, what happened was that when techniques for liquefaction of helium were discovered, they saw strange and very counterintuitive phenomena that was occurring in helium-4 liquid when it underwent through the superfluid transition. It was called superfluid for certain reasons, and one of the reasons was that this fluid would flow without any friction. So it would pass through any orifice, or it would even climb across the walls of the container without any, as if there was no friction. So this was a superfluid state of liquid helium-4, superfluid helium-4, and this Russian gentleman was awarded the Nobel Prize for discovering these effects in superfluid helium. The other thing that led to actually saying that Bose Einstein condensation was responsible for a particular phenomena was superconductivity, which was discovered by Camerlingonis in mercury, as he cooled down mercury after they developed all these techniques of cooling, getting cryogenic techniques which can be used to cool material below 4 Kelvin and all that. He discovered that there is a sudden drop in resistivity and it is very close to zero resistance. Now this phenomena also later was explained by saying that although electrons are fermions, they somehow form pairs, and each pair acting like a single particle, like a boson, and these bosons undergoing a phase transition into a Bose Einstein condensate within the material, and following this similar effects, principles like the superfluid helium, which leads to these electrons flowing almost frictionless within the material, leading to superconductivity and many interesting effects that the superconductors show, like the repulsion of magnetic field or the Meissner effect, and formation of vortices inside superconductors, etc. So these were the first signatures of basically the evidence of formation of Bose Einstein condensate in real systems. Now, for a very, very long time, for like 80, 90 years or even more, there was no other phenomena other than these two cases. Of course, there were thoughts about the superfluid nature of superfluid helium. Such phenomena, people did think that it was occurring in neutron stars and all that, but there was no other system where such a condensation was going to take place, or there was no other system that was found that where a Bose-Einstein condensation would form. Later, what happened was that in the 80s and 90s, there were these techniques for cooling atoms was developed using light, which was basically the laser cooling techniques, which used radiation pressure or the scattering force of photons from atoms to cool down atoms down to extremely low temperatures, to microkelvins and sub-microkelvin temperatures. And these techniques were developed in Europe, Russia, as well as in the US simultaneously for cooling down atoms. Now, when these techniques were developed, suddenly there was a realization that these can be used to actually create a Bose condensate in the lab under extremely controlled environment. And these three gentlemen, of course, there were many other people who also contributed. They did some pioneering work in developing these techniques of laser cooling and trapping of atoms, which actually paved way to create a Bose-Einstein condensate in the lab. And finally, it was successful in 1995. These gentlemen, Theo, Eric Cornell, Wolfgang Ketterle, and Carl Weinman, they actually demonstrated creation of a Bose-Einstein condensate using dilute atomic vapor, not a liquid, gas, or solid, but using atoms in ultra-high vacuum environment to actually bring them together and basically go through these steps of cooling the temperature, increasing the de Broglie wavelength, and making those wave functions overlap and get a Bose-Einstein condensate. So these people, all these three of them got a Nobel Prize in 2001 for developing and demonstrating the first Bose-Einstein condensate created in the lab. So these were the first images of a Bose condensate. So this is basically a complicated experimental setup where you use lasers to cool atoms. I will show you later. And this was a classic cover page of the journal Science, where they showed a Bose-Einstein image of a Bose-Einstein condensate. What this image basically shows is that this is a 3D surface plot of a cloud of expanding thermal cloud of atoms which just follow a Maxwell-Boltzmann distribution. So it expands uniformly when the atoms are not released from a confining environment, if they are just in a thermal state. And this is the image where the atoms go through a phase transition from a thermal state, which is basically a uniformly expanding cloud to a fraction of atoms which expand non-uniformly because of the way the atoms have been confined. And this condensed fraction of atoms, they basically form a macroscopic wave function, which basically the uncertainty of this wave function within the confining trap is decided by the trapping frequencies or the stiffness of the trap along the different directions. And then this is a pure Bose condensate. Now, at the same time, parallelly at MIT in Wolfgang Ketterle's group, they had also observed the formation of Bose-Einstein condensate using sodium atoms. However, they were a little later than what Gila scientists had observed, and they did some of the pioneering experiments with Bose-Einstein condensate. All the features of macroscopic wave function, the phase coherence that exists within the entire condensate, all these features, they actually did a demonstration of that. One of them was an equivalent of a laser. You know, laser is basically like a Bose condensation of photons, because all the photons that are emitted out of a laser, are basically phase coherent, similar to, I mean, like these atoms when they undergo Bose Einstein condensation. Photons also are zero spin particles, and these atoms which are used to form the Bose condensate, their total spin is also an integer spin, although it is for atoms are formed of nucleons and electrons. When you add up the spins of all the particles, the atoms that they use, the particular isotopes, their total spin was an integer spin. Now this is a demonstration of pulse extraction of coherent atoms, and this is an interesting experiment where it demonstrates that if you take a Bose condensate, there is a phase coherence across the entire extension of this Bose condensate. Like if you have a million atoms or about a fraction of a million atoms together in the condensed phase, then there is a phase coherence across all these atoms. Now when you take such a system and split it into two parts, since there is a definite phase coherence, now you bring them together, there will be interference pattern, because if there is any additional phase that is picked up because the way you split it and all that, you bring them together, these wave packets are going to interfere with each other and going to generate interference pattern. So these are the fine lines that you see here are basically, this image is basically a density distribution of atoms. Darker it is, more the atoms. And these lines that you see are basically the maxima and minima of the number of atoms that is formed because of the interference of these matter groups. So these are all the classic signatures of the superfluid state of the Bose Einstein condensate with these atoms. The other thing that one can show with respect to the wave particle duality and the phase coherence of these atoms is, of the condensate is that, say, you can extract in some kind of a quasi-continuous way the atoms from a Bose Einstein condensate, and this line is basically a stream of extremely phase coherent atoms. And this pattern that you see, it is a diffraction pattern of these phase coherent atoms diffracting off a grating that is formed of light. Now, if you look at wave particle duality, light can be reflected, diffracted, etc. using material objects like mirrors and gratings, right? Same thing one can do with atomic matter waves. Okay, you can use light. Light will play the role of matter. Matter will play the role of waves. And here, exactly that is what is happening. So you have the coherent atomic beam which is diffracted from a standing wave of light that is formed here. So the standing wave of light acts like a grating and diffracts the coherent atomic beam, which basically generates this diffraction pattern. So this is a Raman diffraction of an atom laser of light grating. So these are some. This is a result from our lab of this demonstration of the wave particle duality. The other interesting thing that you can do is, like if you have a superfluid in a bucket and you start rotating the bucket, what happens is that there is a phase discontinuity that forms, and there is a singularity at the center that forms, which allows, which basically leads to formation of vortices, which means you will have these small vortices that are formed. And if you take a superconductor, and in a superconductor, these vortices actually create a lattice, like a hexagonally packed lattice, which is called as an abricosol lattice. So those kind of things can be created in with these superfluids. Same thing one can do with these atomic Bose Einstein condensate, and people have created this vortex lattices by just rotating this Bose condensate with forming something like a bucket where this Bose condensate is held and it is rotated very fast. Then you can form, they have shown that one can form these vortices. So these dark spots here are places where there are no atoms, where there is a phase singularity of this superfluid. And one can form, from very few, even from a single vortex to many vortices.